So outlined above is the method of moments, or the maximum likelihood estimation method with steps 1 through 3 written out. We're going to consider this example where the observations x1 through xn come from a uniform distribution on the interval 0 to b. So we have our first step, that's to collect our data. The second step is to form the likelihood function. So we need to know the density function of each observation. Well, it says it's uniform. A uniform is going to be 1 over the length of the interval. The length of the interval is from 0 to b, and that is if x is between 0 and b. Okay, so now we need to form the likelihood function. The likelihood function is of the unknown parameter b, and it's just the product of f of x1, f of x2, all the way up through f of x sub n. So if we write this out, this is going to be 1 over b for x1 between 0 and b. Otherwise, it's 0. F of x2 is going to be 1 over b. Otherwise, it's 0, where x2 needs to be less than b. Otherwise, it's 0. We keep multiplying like this. 1 over b, 0 else, x sub n is less than b, and then it's 0 else. Okay, well, what is this product? You might say that's 1 over b to the n. But that's only if each of our observations, x1 through xn, are less than the parameter b. So that's going to be if the maximum of our observations from 1 to n is less than b. Otherwise, if it's not less than b, if any one of the observations is greater than b, it will be 0, and hence we'll be multiplying by 0, so 0 else. Okay, this is our likelihood function. Let me just draw this likelihood function for us. It's of the parameter b, so that goes on the x-axis. This likelihood goes on the y-axis. B is the input parameter, so it's 1 over b to the n if b is greater than this maximum from 1 to n of each of the observations. So it's going to be something like this, and then it's going to go down as 1 over b to the n. Let's draw that a little nicer. And otherwise, it's going to take on the value of 0. So that is the graph of our likelihood function. This is not differentiable. But the max, we would say, is at the value b, and let me move this b here to resemble the b-axis, at b equals to the maximum of each of our observations. Okay, so that is the location at the max? Well, this is the max right here, to be a little bit more precise, and this is the location of the max. And that's really what we're concerned about, is the location, the value of the parameter that gives us the maximum probability. Okay, so it is b equals to the maximum of each observations. And what I'll just note here is that this is not the same as the method of moments estimator. Okay, so let's prove it. The method of moments estimator would say set e of x equal to the summation from I equals 1 to n of x sub I divided by n. That's the method of moments. And this is just known as the sample average. To figure out e of x, we'd better calculate it. E of x, that's equal to this integral from minus infinity to infinity of x times f of x dx. We wrote out what f of x is. It's only going to be 1 over b when x is between 0 and b. So we need to integrate from 0 to b, x times 1 over b. We integrate x, this is going to be 1/2 times x squared times 1 over b, evaluated at 0 and b. When we plug in b, we're going to get 1/2 times b squared times 1 over b minus 0. So this is just going to be b divided by 2. So if I have e of x, it just says b over 2 is equal to the average. And so this would tell you b is equal to twice the average. This is the method of moments estimator. And it's different from the maximum likelihood estimator, which we have above. So, key point here, method of moments estimation is not the same as MLE estimation. So, the maximum is not equal to twice the average. Okay, thank you very much.